So far we have discussed momentum transfer and heat transfer, and we have also worked what would be the type of transport, how can we express mathematically the transport inside a boundary layer, a hydrodynamic boundary layer, and inside a thermal boundary layer. For the case of hydrodynamic boundary layer, we have seen how to obtain an analytical solution by converting a PDE which was originated out of the simplification of Navier-Stokes equation for flow inside a boundary layer on a flat plate. So, we use the method of combination of variables to obtain not only the velocity Vx and Vy inside the boundary layer, but also the gradients of velocity or at y equals 0, that means at the liquid solid interface, which was then used to obtain an expression for the friction coefficient Cf. We then proceeded for solution of the or treatment of the turbulent boundary layers, and in turbulent boundary layers we saw that the situation became so complicated that it is not possible even to write the governing equations. The statistical it's the having an universal velocity profile which should be valid in all regions of turbulent flow for flow even for a flow over a flat plate is extremely difficult. So, we have seen dividing the flow regime into 3 layers like viscous sublayer, the transition region, and a turbulent core for the case of pipe flow. For each of these regions there was a velocity profile, and there was also an entirely empirical velocity profile known as the 1/7 power law, which can be used to fit the experimentally data, especially for those points situated near the center. However, this expression, even though it fits the data well, it fails on the solid wall because you cannot evaluate the gradient of the velocity at y equals 0, that means on the flat plate using 1/7 power law. That was a major limitation. So, then we proceeded to obtain a momentum integral approach, an integral approach which resulted in a momentum integral equation, and there with some approximation with an assumed value, assumed expression of velocity profile, where the constants were evaluated with the boundary conditions that we have on the plate, namely no slip condition, and at the edge of the boundary layer, that means where the velocity in the x direction would be equal to the free stream velocity, and the velocity profile approaches the free stream with 0 slope. Using these conditions, an assumed velocity profile, we could move ahead to obtain the what would be the boundary layer growth in the case of turbulent flow, and what would be the friction factor expression. We then use the same concept for the treatment of thermal boundary layer. In thermal boundary layer, we saw that it is the equation of energy applicable inside the thermal boundary layer after the standard simplifications, which are boundary layer approximations. This equation is coupled to the velocity boundary layer equation, namely the Navier-Stokes equation for flow inside the boundary layer. The coupling appears because of the appearance of velocity Vx and Vy in the energy equation. So, it is a one-way coupling. We showed in previous classes how to solve this thermal boundary layer growth and the velocity when the temperature gradient at the solid liquid interface through the simultaneous solution of the momentum equation as well as the energy equation. So, for laminar flow, we have obtained an expression for Nusselt number, which is the convective heat transfer coefficient multiplied by a length scale divided by the thermal conductivity of the fluid. This Nusselt number was related to 2 dimensionless groups which appeared automatically through the non-dimensionalization of the governing equation, namely the Reynolds number and the Prandtl number. So, we got compact expressions of Nusselt number with the engineering parameter convective heat transfer coefficient embedded into the Nusselt number. So, that is the H is the one that we would like to evaluate, and the corresponding dimensionless group is Nusselt number. So, we got relationship between Nusselt number, Prandtl number and Reynolds number with a constant in front of it. But that was for laminar flow. I did not say anything about the turbulent flow inside a thermal boundary layer. The treatment of turbulent flow inside a thermal boundary layer is more complicated, more complex, because you are going to have transfer of heat not only by conduction and convection. There will be the formation of eddies, and these eddies would carry additional heat, additional energy for flow for the case when the flow inside the boundary layer turns to be turbulent. So, the presence of the eddies creates or imposes additional problems in the solving the energy equation. First of all, we do not know what would be the right form of energy equation. So, even if we express the energy equation in the same way as we have done for the case of momentum boundary layer, that is in terms of fluctuating components, it is almost intractable. So, we have to think of some ways to use the solutions that we have already obtained for the case of momentum boundary layer, both in laminar flow as well as in turbulent flow. Is there any way to use to project those relations and or correlations for the case of turbulent flow in thermal boundary layer? So, that means I am trying to find an analogy, a logical set of conditions which must be met so that the results of momentum transfer in turbulent flow can be projected and to obtain the results connecting the dimensionless groups, relevant dimensionless groups for the case of turbulent flow inside a thermal boundary layer. And if we can establish this transformation, then the same logic can also be used to obtain the relation between the relevant parameters for mass transfer inside the concentration boundary layer. The way we have the velocity boundary layer, we have seen what is a thermal boundary layer. Similar to thermal boundary layer, I will also have the concentration boundary layer, in which the species concentration would change from some value on the solid plate to a constant value in the free stream of the flowing solution above the solid plate. So, the results of it, so it would be the objective, as I mentioned at the beginning of the course, the objective of this course would be how, why and when we can transform the relations obtained in hydrodynamic part of the boundary solution of the hydrodynamic boundary layer. How can we use that as solution of the thermal boundary layer, and then for the concentration or the mass transfer boundary layer. So, I am not going to do that right now. That would be the last topic of this course. So, I would very quickly go through some of the salient features of the mass transfer process, which is complicated because now we are dealing with mixtures of at least two components, maybe a solute and a solvent. So, at least two species are present in the case where we are having net transport of one species from one point to the other. Now, the net transport of the species from one point to the other, exactly like in the case of heat transfer, it can take place because of actual flow from point A to point B, which carries component 1 from A to B. So, that is due to the imposed flow of the solution from point A to point B, carrying component A from one location to the other, which is nothing but the convective motion of the species, the motion of the species due to convection imposed on the flow field. There would be another way by which mass gets transported, which is similar to the conduction heat transfer by conduction. So whenever there is a temperature gradient, even if there is no flow, we will still have heat transfer because of molecular mechanism. So this conductive heat transfer, which depends not only on the concentration difference but on the gradient of temperature between 2 points, exactly similar phenomena exists for mass transfer as well, which are aptly called the diffusive mass transfer. So in diffusion or diffusive mass transfer, mass travels from one location to the other if there is an imposed concentration gradient. The concentration gradient may exist as a result of several conditions, but if there is a concentration gradient, then mass gets transferred from one point to the other. So similar to heat flux, similar to Fourier's law, similar to Newton's law of viscosity, the mass flux, as in the case of heat flux, is proportional to the concentration gradient. Think of the similarity with temperature gradient. So mass flux is proportional to the concentration gradient, and the proportionality constant with a minus sign, since mass always travels from high concentration to low concentration, the constant of this expression is commonly known as the diffusivity of 1 in 2. It's expressed in the form d with the subscript AB, which is the diffusion coefficient of A in B. Now some of the relations, this is known as the Fick's law of diffusion, which, like Newton's law or Fourier's law, is a phenomenological equation. It cannot be derived. It was arrived by looking at the data of many experiments over a large range of concentrations, and it was found that the mass flux is always proportional to the concentration gradient. So before we use Fick's law and other physical boundary conditions in modeling the mass transfer process, the same way we have done for heat transfer, it would be I would like to go quickly through the relations, the established relations in mass transfer that I am sure you already know. It's only going to be a recapitulation of what you have studied in your mass transfer 1 or mass transfer 2 courses. So our study of mass transfer and modeling of processes involving mass transfer, the mass transport process, we starts with the fact, with the realization that mass transfer is a more complicated process as compared to momentum transfer or heat transfer, because more than one species is involved. So you will have at least 2 species, and in multi-component systems you will have more than 1 species which are more than 2 species which are present in the system, and therefore not only the diffusion coefficients are going to be different, however the motion of the one species, the motion of the molecules of one species in a medium will start to affect the molecules of the medium as well. So when component A is rapidly diffusing through a stagnant medium of B, then the motion of A molecules can create a movement, a flow of the B molecules as well. So mass transfer is definitely more complicated than heat and momentum transfer. So we will quickly first go through some of the modeling exercises of mass transfer, some of the relevant boundary conditions of mass transfer, and then we will come back to the last part of the course, which is analogy between these different processes. So our study of mass transfer begins with some of the definitions that I am sure all of you are aware of or you have studied at some point of time, but I will go through it once again. So the mass concentration is essentially the mass of species I per unit volume of this solution. Similarly, the molar concentration is simply rho I by mi, where mi is the molecular weight of component I. So this is the number of moles of I per unit volume of the solution. The mass fraction is simply divided as the mass concentration divided by the total concentration. the mole fraction xi is Ci by C, the molar concentration of one species divided by the total molar concentration. And of course, if you add rho A and rho B for a binary mixture, then the mass concentration of A and mass concentration of B when added together would give you the mass density of the solution. And this rho A, as rho A is simply Ca times Ma, and Wa, which is the mass fraction, is simply going to be rho A by rho. As with the case of mass density, similarly the molar density of the solution is simply a sum of the individual molar densities, and we understand that Xa, which is the mole fraction, Xa plus Xb equal to 1. The same way weight fraction sum would be equal to 1, and these relations are self-explanatory. So we have all seen these expressions before, and we will see how these expressions will be used later on to understand, to express the mass transport process in a system where we have both convection as well as the diffusive mass transfer. So coming back to some of the other equations, other definitions that one can think of, one uses in mass transfer process, there is something called local mass average velocity, which is simply rho I Vi divided by summation of rho I over all the species. So this is the mass average velocity. In the same way you have the mass average velocity, you can also find out, will also express the molar average velocity, where simply the mass concentration is replaced by the molar concentration. So the denominator is the total mass concentration, whereas the denominator over here is the total molar concentration of the solution. Now whenever a component moves in a solution, then you can either fix the coordinate systems and keep them stationary. So the two definitions of mass average velocity and molar average velocity that I have shown you before are with respect to stationary axis. Now the mass average velocity, it can also be used. Let's say I have a portion of a solution in which there is a diffusing species A, and this entire species has some mass average velocity with which it's, let's say, moving in this direction. However, the species A present in it has a different velocity because it is also diffusing as a result of the bulk flow as well as a result of a concentration gradient imposed on it. So if we want to separate the diffusion from the bulk motion of the fluid, then the diffusion velocity is something which is exclusively due to diffusion for a species A, and therefore the diffusion velocity is expressed as Vi, that is the velocity of the ith species. Subtract from that the local mass average velocity. So the difference in velocity, the additional velocity that the ith component has is over the mass average velocity, is termed as the diffusion velocity. So Vi, the velocity of the ith species, minus the local mass average velocity, is termed as the diffusion velocity of I with respect to V. Now the way you have expressed the diffusion velocity, where the basis is taken as the local mass average velocity, you can take the basis as local molar average velocity, as in V star. So the component velocity, the relative velocity of the component, can be expressed with respect to the mass average velocity or with respect to the molar average velocity. Both are diffusion velocities. One is with respect to V, the other is with respect to the molar average velocity. So these are the two diffusion velocities that are quite commonly used for for mass transfer. And this velocity, the velocity of this, if you expand it, it's simply going to be 1 by rho times rho A Va plus rho B Vb, in which if you take the ratio of rho A by rho, it's simply going to be the the weight fraction of component A, and similarly V star, which is the local molar average velocity. If you expand this, it's simply going to be 1 by total concentration, then molar concentration of A, molar concentration of B, and the velocities of A and B, and Ca by C is nothing but the fraction, the mole fraction of component A and mole fraction of component B. So these two relations directly follow from the definition of the mass average velocity or the molar average velocity. Now, since we have defined the diffusion velocities in this way, now the diffusion velocities can then be converted to fluxes. So one would be a molar flux and the other would be a mass flux. So in terms of stationary coordinates, it's simply going to be rho I times Vi if you express it in terms of mass, or if you express in terms of moles, it's simply going to be Ci Vi. These Vi's are with respect to stationary coordinates. When you bring the same mass flux or molar flux and take the average velocity V bar to be the basis, so relative to the mass average velocity, the mass flux or the molar flux denoted by J or capital J for the ith species is simply going to be rho I times the relative velocity, where for the relative velocity we use the mass average velocity. So it can either be expressed in terms of mass or it can be expressed in terms of moles. Same thing if we do in terms of molar average velocity. So this is in terms of stationary coordinates where the velocity is 0, where V is 0. So it's rho I Vi. If I have a mass average velocity and I express relative to the mass average velocity, it's simply going to be Vi minus V. If I do it in terms of molar average velocity, it's going to be Vi minus V star for the case of mass, and for the case of moles it's simply going to be Ci. Now this flux, be it mass flux or molar flux, is generally expressed, the molar flux where J star, if you look at J star, this is the molar flux of the ith species when the flux is relative to the molar average velocity, which is, so Ji is equal to Ci times Vi minus V star. This molar flux is proportional to the concentration gradient. That is the statement of Fick's law. So Fick's law essentially tells us that the molar flux Ji star is proportional to the concentration gradient. So Fick's law is simply the flux, molar flux of component A when expressed with respect to the molar average velocity is simply minus dAB times divergence of Xa. So if C is constant, I can put C inside. It is simply, the other way of writing it is times Ca. So this, for a rectangular coordinate system, can be written as minus dAB times del Ca del x plus del Ca del y plus del Ca del z. So see the similarity that we have for the with heat transfer and with mass transfer. So this is the statement of Fick's law, and from our definition of molar flux, this is the definition of the molar flux when expressed in terms of V star. So I expand it, and CAVA is nothing but the molar flux of A, and then when you express this V star, the formula would simply be CAVA plus CBVB by C. Ca by C is the molar the mole fraction. So your Ja is equal to Na minus Xa times Na plus Nb. Plug it in here, and what you have is another form of Fick's law. So this Na is relative to stationary coordinate and what it tells is that the molar flux of component A relative to stationary coordinates from here is a sum, is an algebraic sum of xa times Na plus Nb, where xa times Na plus Nb is the flux due to the bulk motion of the fluid. So, Ca times V star denotes the molar average velocity. So, if you have a bulk velocity present, bulk motion present in the fluid, it is also going to contribute to a flux of A. As I said, the species A can move from point A to point B if there is a bulk motion. There may not be any difference in concentration. So, a sugar solution, a constant concentration sugar solution may be forced, may be allowed to move from point A to point B by imposing a pressure gradient. There is no diffusion since the concentration is the same everywhere, but what you have is a bulk motion of the sugar molecules from point A to point B. So, this kind of bulk motion imposed by the flow only is the significance of the first term that we have here, which is xa times Na plus Nb. So, this is due to bulk motion. Sometimes in addition to bulk motion or even in absence of bulk motion, you have concentration difference. So, if you have concentration difference, or the more correctly, if you have a concentration gradient present in the system, then this is going to give rise to a diffusive motion of A, species A. So, the total effective motion of species A is the algebraic sum of the species movement due to bulk motion and or the species movement due to a concentration gradient imposed due to certain conditions present in it. So, therefore, the problem of Fick's law is to be resolved. The first thing that needs to be resolved is how to get rid of Nb from the expression of Na. So, Na is xa times Na plus Nb minus dAb del of concentration of A. So, first of all, it may be mentioned that it is a diffusion only process. That means there is no imposed bulk flow. So, if it is a diffusion only process, then the first term on the right hand side, which signifies bulk motion, can be dropped. So, that is one way of getting rid of Nb, which is the unknown, which appears in this expression. So, if it is a bulk motion, if it is a diffusive motion only situation, then this can be dropped. In some cases, there would be a relation between Na and Nb which arises due to some other factors. For example, it could be a case of equimolar counter diffusion. That means, for 1 mole of A moving in this direction, 1 mole of B is moving in the opposite direction. So, if this is a case of equimolar counter diffusion where Na is going to be equal to minus Nb, for that specific case Na is going to be equal to minus Nb, and therefore, this term, the contribution of this term would be 0. So, the expression would be same as that of diffusive motion only situation, but for a different reason. Since it is a equimolar counter diffusion, Na and Nb would cancel out each other. There are in some cases the stoichiometry of the reaction, if it is a reacting system, let us say 3 moles of A comes and reacts on a catalyst surface, generating 2 moles of B, which then travel in the reverse direction towards the bulk. So, for every 3 molecules of A coming to a specific direction, 2 molecules of B would have to travel in the opposite direction at steady state in order to maintain the concentration at each point independent of time. So, the concentration of A may vary, concentration of B may vary, but the concentration at a fixed location will not vary with time. So, that's what the steady state is. So, in some cases, stoichiometry of the reaction or stoichiometry of the reaction taking place between 2 reacting components would give you some idea between the relation between how Na is related to Nb. So, in absence of any such generalization, any such simplification, the expression to be used for the molar flux of component A will consist of 2 terms, one due to bulk motion and the other due to the concentration gradient. So, this DAB, which is the diffusion coefficient of A and B, they behave slightly differently for gases and for liquids. Okay. So, both of them increase with an increase in temperature. So, as the temperature increases, this DAB, it's a function of pressure, temperature, and it's also a function of, it could be a function of composition of the gas mixture. So, the gases, for gases and liquids, with increase in temperature, DAB increases, and at low density it's almost composition independent for the case of gases. So, what we have then, we need to see the similarity between DAB, which is the mass diffusion coefficient expressed either in terms of mass or in terms of mole. Compare that with gamma, which is mu by rho, and compare that with K by rho Cp, which is alpha. So, if you compare DAB, the diffusion coefficient of A in B, mu by rho, which is the kinematic viscosity, and K by rho Cp, which is the thermal diffusivity. So, momentum diffusivity, thermal diffusivity, and mass diffusivity all will have units of meter square per second. So, these 3 are similar in nature. The mass diffusivity, the momentum diffusivity, and the thermal diffusivity, they have the same unit as meter square per second, and all of them denote the transport of mass, the transport of momentum, or the transport of energy when you impose a concentration gradient, a velocity gradient, or a temperature gradient. So, this would be the beginning, the start of the analogy, finding the analogy between different processes: heat transfer, mass transfer, and momentum transfer. But before we reach that point, what I would do in the subsequent classes, 3 or 4 or 5 classes after today, is to show you examples by which, first of all, a shell component balance can be used to obtain the concentration profile of a specific component in a system where it's a diffusion only process, where both diffusion and bulk motion, convection is present, and different ways by which Na can be related to Nb, the molar flux of A and the molar flux of B. What is the relation between them apart from counter diffusion, equimolar counter diffusion, and so on. And finally, the like heat generation in the case of energy equation, we can also have generation of a species due to reaction, generation or depletion of species due to reaction in a medium in which A is diffusing. So, if A is diffusing and as it diffuses, it reacts with another reactant B present in it, then A is going to get depleted as it moves in the solution. So, reaction, chemical reaction, homogeneous chemical reaction can act as a source or a sink term in the mass balance equation. So, when we write the shell balance of shell component balance, the same way we have done for the previous cases, heat transfer and momentum transfer, the source or sink term, for example, a nuclear heat source or an electrical heat source, the equivalent of that in the case of mass transfer would be if there is a reaction which is consuming A or a reaction which is producing A in the entire domain of transfer of A from point 1 to point 2. So, a homogeneous reaction would appear as a source or sink term in the governing equation. So, contrary to that, if it is a heterogeneous reaction, that means if it is a, let's say it is a catalytic reaction where this is the catalyst surface and the reaction of A getting converted to B is going to take place only on the catalyst surface, it is a heterogeneous reaction. Therefore, A has to diffuse and reach at this point where it gets converted to B, and the products will diffuse back to the mainstream. In that case, since in the path of diffusing A, it does not encounter any reaction, generation or depletion, the generation or depletion takes place only at a specified location, that is on the catalyst, heterogeneous reaction. This condition would appear as a boundary condition in the governing equation. So, we have to keep in mind the difference between the heterogeneous reaction and the homogeneous reaction, one in which it appears as a source or sink term in the governing equation itself and the other where it appears as a boundary condition. So, we will see examples of that, examples of modeling the process in the coming 4 or 5 classes, and then we will finally move to the final part of this course, which is to evaluate the analogy between heat, mass and momentum transfer.